Hi guys, my name is Peter C. Dogba Jr., math instructor at the University of Liberia and your math tutor. In my today's lecture, I will be discussing differential equation, and particularly I'll be looking at differential equations of first order and first degree. Now that is using the method of separation of variables to solve a first order and a first degree differential equation. Now, we said the first order and first degree differential equation is of the form dy by dx equals to f of x comma y, that is a function in x and y. It can also be written in the form of f prime of x is equals to f of x comma y, or it can be expressed in the form of m dx plus n dy equals to 0, where m and n are factors in terms of x and y. Like you have something like x plus 1, like you have something like x plus, like you have like 2 plus y. So these are expressions in terms of x and y. And then you also have it of this form. Now this one is clearly expressed when we have m of x comma y, a function in x and y, times dx plus n, a function in x and y, times dy. Now, so we want to look at the first step wherein we can apply separation of variables, and we will look at another case wherein separation of variable is not, it cannot be implemented at the first look of the problem, but we can reduce it to separation of variable. So we said whenever it is possible to separate all of the functions, so whenever we have an equation, a differential equation, and it's possible to separate all of the functions in x and separate all of the functions in y, that is, when the functions in x are separated, there is the derivative notation being attached to it, that is dx. And when the function in y are all separated, the derivative notation as well, dy, is attached to it. So when it can be separated in such a form, it means you can apply separation of variables to integrate that or to solve that differential equation. So that's exactly what we meant. We said whenever it is possible to separate all functions of x along with the x on one side of the equation, and the same with all functions of y along with dy on the other side of the equal sign or of the equation, then we say that the variables are separable, and we can therefore find its solution by integrating both sides of the equation. So you see, it's well explained. So we're just going to go about now looking at a problem and see how best we can be able to solve using the method variable separable. So assume you have this kind of problem like this, dy by dx, and then you have x and y, wherein x is a function in all x, y is a function in all y. So we can cross multiply. So if we cross multiply this time this, this time this, so you will have 1 times dy is dy, and then the x times xy is just equal to x y dx. Now, since this is the x and this is the y, right, we need all of the variables that should be attached to this dy should all be in y, and all of the variables that should be attached to this dx should all be in x. So to do that, we say, since we need x here, we maintain this x, we get rid of this y. Now, since we also need, let's say, okay, so now the coefficient is just 1, so this is it. So this y, we cancel this y, that's all. Then you'll be left with dy over y equals x dx. So when your differential equation is of this form, we say it is in in a form wherein the variables have been separated. Then we can integrate both sides to find our general solution. So we take the integral of this side, we take the integral of this side. So the integral of 1 all over y is just the ln of y equals, and the integral of x is just x raised to the second power divided by 2 plus some arbitrary constant c. Now, so I just want to tell you this thing. The arbitrary constant c can be any expression. We can rewrite c in any form, but it should always be c. It should always be a constant. That's what I meant. It should always be a constant. So it can, what if we had c and then we probably want to multiply to get rid of this 2 in the denominator? We'll multiply this whole thing by 2, and we got 2c in this problem now. So 2c is still an arbitrary constant. Even if we're to differentiate this, the derivative of 2c is equal to 0. The derivative of c is equal to 0. So even if you had 2c, at your final answer, you can still represent that 2c to just be c, or to just be d, or any arbitrary constant. So remember, the constant, we can represent it in several ways so that we'll be able to simplify the problem. It makes no change to the problem. Now, if you even had a case wherein you want to rewrite the constant c as some ln of e, because we know that ln of e is equal to 1. So if you want to rewrite it in that form, it still remains a constant, right? So the intent is to be able to simplify our final solution. That's a no difference. So let's erase. So for that problem, now we have the ln of y is equals x squared over 2 plus c. So we want to get rid of this 2, we can multiply all sides by 2. Therefore, we have 2 ln of y is equals 2 times this 2, when this 2 cancel, you're left with x squared, plus 2 times c is just 2c, right? So now we can decide to put everything on one side of the equation and make the second part of the equation to be 0. So the right hand side is 0, and then we express every other term on this side. So you have 2 ln, let's say ln of y minus x squared plus, now it's minus now, minus 2c, right? So you can rewrite this entire 2c portion as just c. Ln of y is equal to minus x squared minus or plus c, because minus c plus c is still c, the arbitrary constant, or equals to 0. So this could be your general solution, or you can further reduce it, send this 2 to the power of y and further reduce this problem. But this is your general solution. This is how we find the general solution of a differential equation using separation of variables. So we're going to dive into solving more problems. This was just the introductory aspect, and we're going to dive into solving more problems and simplifying them in simplest form, in the simplest of all forms, so that we don't even arrive in a kind of answer like this. Because in some cases, we'll be solving for y, we will be directly solving for y. So we'll show you all of those cases that we can solve for y when this y is within this ln and everything. So thanks ever so much for watching. Please subscribe to our YouTube channel, and see you in our next lecture. Thank you.